The college algebra course is basically a study of the major types of functions. So we are going to go down a list of types and take a look at each one. The first type of function in that list would be a linear function. So let's take a few minutes to talk about those. A linear function would be a function of the form f of x is equal to ax plus b. Now this is the general form that we use to describe a function that is linear. You've probably seen the y equals mx plus b. This is essentially the same as that. Y and f of x are interchangeable. And in this format, a and b are real numbers, just like m and b would be real numbers, so they're very much comparable. A function, a linear function has a graph that is a line. So we can make the graph, and when we do, we know the shape of the graph is going to be a line. The way we can identify the equation for a linear function, x and y will be variables, or we could use f of x. The x and the y, though, will be in separate terms. They'll only be raised to the first power, and that's going to be different than some of the other equations we look at later on in the semester. And if there are fractions, we may have numbers in our fraction, but the variables will never be in the denominator of the fraction. Okay, so the next step maybe is to look at the different formats that we can write an equation of a line with. The first of those is the slope-intercept form that we've mentioned already, the y equals mx plus b. So I think this is probably something that you've seen before, practiced before, but let me just touch on some of the basics, I guess, of the y equals mx plus b. The b, if we form it into a point, is the y-intercept. The y-intercept is the point where the graph touches the y-axis. And this fixes the location of the line. So if we want to find the y-intercept, if it's organized like this, we can just pull out the value of b. We don't have to do any work for that. If we don't have it organized like this, to solve for the y-intercept in general, and this would be true for any kind of equation, we're going to set x equal to 0 and solve for y. And then we'll form it into a point that looks like this, where x is 0 and y is some number. Okay, so that's the y-intercept. The next key part of the slope-intercept form would be the slope. M is the slope, and the slope measures the steepness or the slant of the line. And the slope is kind of interesting because all in one number we can tell a lot of things about our line. We can tell whether it's going up or going down, whether it is a gradual increase or a quick increase, right? All of that is summarized in one number, which is kind of interesting. There are lots of ways to describe the slope of the line. We do have a formula, and so the formula that we usually use for the slope looks like, I'll just write it like this. So if we have, maybe I'll write these points off to the side. If we have 2 points on the line, x1, y1, and x2, y2, and I always like to point out those 1s and 2s are not exponents here, they're subscripts, just so that we can kind of identify this is point 1 and this is point 2. Okay, the slope is the difference in the y's, so y2 minus y1 over, or divided by, the difference in the x's, x2 minus x1. That's the formal formula. There are other ways that we could talk about the slope. So let me list a couple of those down below. You've probably heard the slope described as the rise over the run. Right, so the slope really tells us how fast we're either rising or falling as we move from left to right. Another way that it's described is the change in y over the change in x. And we could use that same idea and kind of represent that with symbols as well. So the change in y, we usually use a delta y. And the change in x, we can use a delta x. I don't know whether we use that as much in our college algebra course, but if you're going on to take other math classes, you may see that notation. Okay, so that's kind of a basic introduction to the y-intercept and the slope. Those are two things that are kind of come up a lot in this chapter. Next, we want to talk maybe a little more specifically about what kinds of slope we can have. There are actually 4 types of slope that we can come across for our line. The first one being a positive slope. So if we have a positive slope, that means as we move from left to right, our line is going up, basically. And so you can use a couple different words for that. You could say it's a rising line, or you could say that it's increasing. So that's if our slope is a positive number, right? The opposite would be true for a negative slope. As we go from left to right, our line is going down. The y value is decreasing. So you could say that that was a falling line, or you could also call it decreasing. Okay, and then there's 2 other possibilities, right? If you think of the formula again for the slope, let me put that right here so we can look at it. So the other 2 possibilities happen when either the numerator for our slope formula or the denominator becomes 0. So let's start with the numerator. So if the numerator, right, the y values happen to be the same and we subtract them, then we get 0 on the top. And something else in the bottom, maybe we have for our slope 0 over 5. Okay, so 0 divided by anything is still 0. So if our slope is 0, I like to describe it this way, just to fit it in with the mx plus b, right? So 0 is an actual number we could use. So if I put 0 in for m, right, the 0 slope is multiplied by x, so that whole term is actually 0, and I get something that looks like y equals b, or y equals some number, whatever the y-intercept happens to be. Okay, so let me give you a quick example of that. Let's say we had the line y equals -2. We haven't really said what kind of line this is yet. Okay, so let me kind of describe to you. I use this as a memory tool to help me remember which is which. Okay, so when I see an equation like this, there's no x in this equation because the 0 slope has sort of canceled it out. In that case, the x can vary. It can be any number we want, but the y value is always going to be fixed at -2. So I can pick any x numbers I want. I like to use -1, 0, and 1. And for any x I pick, the y is always going to be the same. For this particular example, it's going to be -2. If I plot those points on a graph, I can give you a really good hint about what kind of line this is. So if I plot those, I have -1, -2, 0, -2, and 1, -2. Notice these are all lining up horizontally because they all have the same y value. Okay, so if the slope is 0, we have an equation that looks like this, y equals some number, and it's a horizontal line. Okay, and that's kind of a special case, but now you know what that looks like. The opposite of that, maybe you could say, would be if the slope were undefined. So if the slope is undefined, that's going to happen when the two x values in the bottom of our slope formula happen to be the same. And so because we can't divide by 0, we get a slope that's undefined. Now because the slope being undefined is not a number I can plug in, this one is not really going to match up with the y equals mx plus b format. But it is sort of similar to the horizontal line we have here. This one is a y equals some number. The undefined slope is an x equals some number. So you could use a variable there. You could say x equals a, or just know that there's going to be a number there. Okay. The way I remember these back and forth, let me just write this. So this one is going to be a vertical line. If the slope is 0, think of that like flat ground. There's no steepness, there's no slant, it's horizontal like the horizon. That's how I remember that. Okay. If it's x equals some number, or if the slope is undefined, I think of that almost like infinite steepness, like the drop off of a cliff would be vertical. And so that's a vertical line. So let me give you another example, kind of a similar type of analysis here so that you can see what a vertical line, how the graph would look. It's kind of the opposite phenomenon here, right? So now I have x equals 3. So now my x value is fixed at 3. And because there's no y value in the equation, y can vary to be anything we want. I'm going to use my same -1, 0, and 1 because I think that's convenient. But you could pick any number you like. And we could plot those points to help us remember whether this is vertical or horizontal. So we have the point 3, -1. We have the point 3, 0. And 3, 1. And you can see that if the x values are all the same, it's going to line up vertically. Okay, so here's a question for you. Is this graph we've just drawn with the equation x equals 3, is this a function? Think about the vertical line test. Definitely not, right? All of these points have the same x and different y's, and there's going to be infinitely many of those. So yes, a vertical line would not be a function. Okay, so that gives you a little bit more detailed explanation of slope. 4 different possibilities, right? Increasing, decreasing, horizontal, and vertical. Now let's take a minute to just look at an equation of a line. I want to point out some of the details and give you a chance to see how everything connects together. Okay, so here's an example of a linear equation. It's not in y equals mx plus b form right now. This is actually in general form. But we have x plus 5y equals 17. And I thought maybe we could take a second to find the intercepts. That's going to be a tool that we use for a lot of different types of functions, not just linear functions. So for the x-intercepts, we didn't really talk about that one. This is one we're going to set y equal to 0 and solve for x, or find x. The y-intercept we did talk about, and that's basically the opposite. We're going to set x equal to 0 and find y. Let's do that for this equation. Okay, for when it's in this format, it's kind of easy to do. You could use that cover method, which is a lot easier to do on the whiteboard because you can put your whole hand over it, but you can put your finger over it, I guess. Okay, so if y is 0, this part is 0, so essentially x is going to be 17. Oops, let's write it out. Since this is 0, x plus 0 is just x. And so the x-intercept would be the point 17, 0. And I do think there is some value to listing it out as a point. Okay, and then the y-intercept would be the opposite of that. So now we're going to make the x 0. So we have 5y equals 17. We can divide both sides by 5. Okay, and we want to write that as a point as well. Now you're welcome to either leave this as a fraction, or if you'd rather write it as a decimal, I think this goes in 3 times, it ends up coming out to 3.4. Okay, so our y-intercepts would be the point 0, 3.4. Okay, so we could use those 2 points alone to draw the graph, right? We could plot those two and draw a line through the 2 points we have. I want to show you some other things, so we're going to do some other things in between doing this and the graph. But you could do that. If your task was to draw the graph, you could use those 2 points and be done, right? Okay, what I also wanted to do was give you a chance to see a table of values for this. Let me copy down the equation again. Because there is something interesting that happens when we have a linear relationship in the table. So just so that you can see the pattern that I'm trying to point out to you, I'm going to set up the table where the x's jump by 5s. So we've got -5, 0, 5, 10, 15 maybe. Okay, so you could take these, you could plug them into your function for x and solve for y. So I'm going to let you do that on your own. Let me just show you what you would get if you did that. If I plug in -5 here for x, right, and I add it over, divide by 5, and solve for y, I'm going to come out with 4.4. If I plug in 0, which actually we just did up there, right, I got 3.4. If I plug in 5, the same way, turns out I come up with 2.4. Can you see where this is going? If I plug in 10, what do you think I'm going to get? I think you're right. I'm going to get 1.4. Okay, and this pattern continues. If I put in 15, I'm going to get 0.4. And that's not a coincidence, right? So for a linear relationship, if I have a steady change in x, like I have here, because I set up my x's that way on purpose, from one to the next, I'm adding 5 all the way down. Then I'm also going to see a steady change in y. This change in y, I'm subtracting 1, going down all the way. Okay, and so when I have a linear function, I usually say, well, let's write this out because this is important. So a linear function has a constant rate of change. Okay, another way to say that is we have a steady change in x produces a steady change in y. And that's how we can decide if a function is linear. So if I'm given a table of values, if I want to decide if that table is, if those points are going to line up straight in a line, I can look for this. Do I have a steady change in X? And if I do, does it produce a steady change in Y? And if it does, then I know that these points are going to line up in a line. Okay, this word here, rate of change, is essentially another word for slope. So if we wanted to find the slope for this function, it's not organized as mx plus b right now. We could use the idea of the change in y over the change in x. What is the change in y? Well, that's this -1. And what is the change in x? That is this +5 all the way down. So even though I didn't use the formula, I'm still using that same idea to identify the slope. And I don't have to do a lot of calculating. I can see that in the table. Okay, so we've talked about the intercepts, we've talked about the slope. Now let's kind of integrate that with the y equals mx plus b. Let's see if we can. Okay, so now let's take our equation. Let me write it down again. Here it is. And let's solve for y and write our equation in slope-intercept form. Excuse me. Slope-intercept form would be the y equals mx plus b. Okay, so we're not plugging in any numbers here. We're just rearranging the equation so that y is by itself on one side. And we'd like our final answer to be in this format. So to do that, we're going to subtract our x over to the other side. I like to put that x in the front because I'm trying to make it look like mx plus b. And when this is just 1x, so when I subtract it over, technically this is -1x. If you want to put the 1 in, if that makes it, it might be easier to look at. Okay, and then to get y by itself, I'm going to divide everything by 5. If I divide by 1 on this side, I have to divide everything on the right-hand side. So you can either write it as a big fraction over 5, or you can write it individually if you want, because both of these parts are going to be divided by 5. So the equation of my line, I'm just going to write it down here, becomes -1/5 x plus 17/5. These parts should look familiar, right? We just talked about the slope, and we said it was -1/5. Earlier we solved for the y-intercept, and we got 17 over 5, which is the same as that 3.4. Okay, so all of that goes together to make, right, so calculating the slope, whether we use a table or an equation, that same slope's going to show up in this mx plus b. Now, if we draw the graph of this line, let's see if I can bring in our table. See if we can put everything together on one screen. Maybe. Okay. There we go. All right, so since we set up our x's by 5, we might want to mark off our x axis in units of 5. Okay, and then we'll keep these the same. I mean, units of 1. 1, 2, 3, 4, 5. So at -5, we're at 4.4, and we're just going to estimate. At 0, we're at 3.4. 5, we're at 2.4. 10, we're at 1.4. 15, we're at 0.4. I don't have this on my chart, but way back at the beginning of this example, remember we found the x-intercept was at 17, so that's right about there. Okay, and we don't need this many points, but I figured we'd just use what we had. And we could draw a straight-ish line through those points. I probably could have used a ruler to make that a whole lot straighter, but I think you get the idea. Alright, well I hope that gave you kind of a thorough look at a linear equation. We kind of did each part individually, and I hope you can see how those tie together and make those connections. That's really where the learning happens. Good luck with your linear equations. I hope this helped you understand what they look like.